Today we want to continue talking about sequences, series, and power series, but first we want to clear up a homework question from Chapter 8, Section 2, and it's problem 5. We have a function defined with parametric equations, and it's an arc length question. So if we have parametric equations, a curve defined by x equals some function of t and y equals some other function of t, for t between a and t, then the arc length, or the distance traveled, is going to be the integral from a to b of the square roots of dx dt plus squared plus dy dt squared. With respect to t. And what we're looking at is the distance formula if we just chop the curve up into small little straight line segments. So what we have is some curve, and every time I draw this curve, there's like this really straight segment in here, and I need it to be curvy, but I'll just have to pick a point where things are a little bit more bent. So what we can think about is making a little triangle where there's some dx dt is just how things are going in the x direction. And then there's, at this point, a dy dt, which is how things are changing in the y direction. And so we could think of just breaking this up into horizontal and vertical components. And we're just saying, instead of this curve being all curvy, let's just make a bunch of straight line segments out of it. Because that's what we do. We take the continuously changing thing and make it not continuously change. That's the whole calculus assumption. We make the continuously changing thing and say, instead of making it continuously change, let's just make it an easy thing for us to calculate. And that would be like the distance of a straight line segment. And so if we combine these two, we just use the Pythagorean theorem, where dx dt is what is the length in one direction, dy dt is the length in the other direction. So this is the length that we're going to go. So for Chapter 8, Section 2, Problem 5, this is the formula that we want to use. Where's that? There we go. So for the actual problem, we have x is 9 cosine of t and y is 8 sine t. So the actual problem was x equals 9 cosine t and y equals 8 sine of t for t between 0 and 2 pi. So we have this ellipse, and we want to find the circumference of this ellipse. It's an ellipse because x is cosine and y is sine. That's going to make us go around in a circle. But if we adjust the coefficients, 9 cosine of t means that the radius in the x direction will be 9, or, well, not really a radius because it's not a circle anymore. It's going to have a 9 left to right and an 8 top to bottom. So instead of going from -1 to 1 and then -1 to 1, in the x direction, it goes from -9 to 9, and in the y direction, it'll go from -8 to 8. But it'll still trace the same path counterclockwise around once. 0 to 2 pi is around once. So once we have x is 9 cosine of t, we just take the derivative. So dx dt, dx dt. The derivative of cosine is negative sine, so -9 sine of t. And dy dt is 8 cosine of t. And so we just need to set up the definite integral. So the distance is the integral from 0 to 2 pi, the square root of dx dt squared plus dy dt squared. And we just make our calculator do this. We can simplify it maybe if we want. Any questions?
Professor, the square root where dx and dt are squared, is that the standard equation for finding distance of or length in a triangle?
Yeah, this is just the distance formula.
Okay, just wanted to make sure. Thank you.
Yeah, it's just the distance formula, or which comes from the Pythagorean theorem. We're making a triangle. The length here is going to be dx dt times the time, and then dy dt multiplied by the time. And so we'll have these two lengths squared. And then we use Pythagorean theorem for the. And what we're doing is we're viewing this. We're viewing the curve instead of as a continuously changing curve. We're viewing it as a bunch of line segments. So we're viewing it as a bunch of line segments. And then we're just adding up we're using the distance formula to add up the lengths of all those little line segments. And then we're making the line segment shorter, and then we're just using an infinite number of infinitely short line segments.
Thank you.
Any questions? All right. So let's continue to talk about series and convergence of series. So yesterday, we introduced the idea of the alternating series test. So for convergence, one way to think about this convergence question is for a series to converge, well, for a series, let's say AN, to converge, we need two things. The first necessary condition was the limit of the terms has to be 0. But this is not enough. We can't get by just saying that the limit of the terms is 0, because sometimes the limit of the terms is 0 and the series diverges. So we need something else. We need something to indicate how things are getting to 0, or how the terms are going to 0. That something else could be the terms are going to 0 faster than 1 over n. And we have ways of quantifying that by comparison to a p-series or with a geometric series. Another something else that we acquired yesterday was alternating. If the terms go to 0 and the terms decrease and the terms alternates, then we get convergence. So this something else business could be the terms go to 0, they go to 0 faster than 1 over n. That's kind of a comparison. That's a comparison test question. The terms are going to 0 faster than 1 over n. Then another thing that we get is alternating. So that's the alternating series test. So a good example of this is the harmonic series. The limit of the terms is 0, but the series diverges. But the alternating harmonic series converges. So even though the terms in absolute value are not getting to 0 faster than 1 over n, that's just how fast they're going. By making them alternate, we get the sequence. We saw that the sequence of partial sums converged. So that was just the spring doorstop. It's just going back and forth. And that's our proof of the alternating harmonic series, or the alternating series test. So remember, we always phrase these as tests. These are tests for convergence, but the tests don't work if we don't already know whether something converges or diverges. Also note that the alternating harmonic, I keep calling it the alternating harmonic series. The alternating series test only concludes that the series converges. You can't say something diverges by the alternating series test. It only has one conclusion, and that says converges. So let's review what the alternating series test claims. Oops. Let's consider the alternating series. So note, when I set this up as an alternating series, the AN has to always be positive. So AN is going to be positive for all n. That's what makes it alternate. So this change in sign only comes from the -1 to the n part. If the terms decrease, and the terms decrease to 0, and the terms alternate, then the series converges. So here's the alternating series test. Notice that the only thing the alternating series test can conclude is a series converges. If we're missing one of these three things, if we're missing the limit of the terms being 0, then the series diverges, because this is a necessary condition. So one thing we wouldn't be able to use the alternating series test for is where the limit of the terms is 0, but the terms themselves don't decrease. So even if a series is alternating, if the terms aren't decreasing, then the alternating series test is not going to work. But what this does provide us with is that alternating can make things converge. Alternating is a step towards convergence. Our favorite example of this is the harmonic series. So the alternating harmonic series converges. The alternating harmonic series converges. The limit of the terms is 0, the terms are decreasing, and the terms are alternating in sign. Therefore, by the alternating series test, the alternating harmonic series converges. So that's what we proved yesterday. The thing to note is the alternating harmonic series converges, but if we take away the alternating part, the harmonic series, the regular harmonic series, diverges. So recall, the harmonic series just the sum of 1 over n diverges. So the alternating harmonic series converges, but it doesn't converge if I take away the alternating part. So this is a type of convergence called conditional convergence. So the alternating harmonic series is said to be conditionally convergent. There are two kinds of convergence. I mentioned at the beginning of this whole chapter, there were two kinds of convergence for series: conditional convergence and absolute convergence. So conditional convergence means a series converges, but if we make all the terms positive, then the series diverges. If we can make all the terms positive and the series still converges, then it's called absolutely convergent. So let's say a series, we say if a series AN converges, but the series in absolute value diverges, then the series AN is conditionally convergent. The way to think of conditional convergence is we need all those negative terms to get convergence. We need to be subtracting a bunch of those terms. We need the negative terms for convergence. So the way to think about conditional convergence is to think we need the negative terms for convergence. If we make all the terms positive, if the series converges, if we make all the terms positive, then we don't need the negative terms for convergence, and we say the series is absolutely convergent. So if the series in absolute value converges, then the series AN is absolutely convergent. We're not just emphasizing with absolutely, it's actually in reference to the absolute value signs. So when we're talking about convergence, we can't be like, oh, we can't use absolutely in the affirmative. We're like, oh, does this converge? Absolutely. It's like, oh, no, you can't use that anymore. If you don't want to just say yes, then stop trying to be so extra. Just say yes. But you could be like, oh, totally, if you wanted to be like all extra and casual about it. So there's a difference between absolute and conditional convergence. Absolute convergence is a stronger condition. It is harder to make things converge if everything is going to be positive. You make half the terms negative, kind of dubious to call it half because there's an infinite number, but if you make half the terms negative, and that's what you need to do to get convergence, that's a weaker condition. So absolute convergence is a stronger condition. It's a stronger condition. It's more restrictive. It's like the difference between a continuous function and a differentiable function. Differentiable is a stronger condition. It's harder to get differentiability than it is to get continuity. So where this matters is that we really want to make sure that we distinguish between when we need the negative terms for convergence. So for example, if we have an alternating series, an alternating 1 over n squared. So we start off with 1 over n, 1 minus 1/4 plus 1/9 minus 1/16, and so on. We could, since this series is alternating, use the alternating series test to show that it converges. But we don't need to do that. We get a stronger condition, and this is the thing that we want to be on the lookout for. Notice that if I take the absolute value of minus 1 to the n plus 1 over n squared, the absolute values will take out the alternating parts. So I don't need the alternating to get convergence. This series is absolutely convergent. Blue conclusions. So the series, the alternating over n squared, is absolutely convergent. So we don't want to bother with the alternating series test because we don't want to rely on the alternating part for the convergence. Go right for the bigger convergence when you got it. We also, I'm just going to preempt this one right now. Well, I'm just going to tell you the cruel things that you can do with this kind of thing. Give a quiz with where everything that's alternating, a bunch of series that are absolutely convergent, and make them all alternate. And then students will invariably pick some of them to be conditionally convergent because they think conditional convergence is going to have to show up. Because it's like a true-false test. If I give you 10 questions, true or false, you're going to want to make 5 true and 5 false. At most, you'll go for a 60-40 split. Some of you that are really bold might go for a 70-30 split. But that means that the highest score is still going to be 70% when I make 10 things true. It's like when you're taking a multiple choice test, it's like, well, if you don't know, just put C. Because C is like the average of everything. It's like C, the average of A through E. And so you put C. That's terrible. Averages shouldn't be used as much as we use averages. C for correct. Maybe that must be the thinking. C for correct. But that's if you just want to pass. If you want to get an A, then clearly you need to put A. And I bet I could get a lot of people to stop putting C all the time if instead of A, B, C, D, E, I put A, B, C, D, F. Then I bet you'd put more A. So I don't normally give multiple choice tests where there's an A through an E. But if you're taking a multiple choice test, the answer is almost never C. I have an anti-C bias in my writing of multiple choice tests. In my grading, I have a C bias. So I don't ask this question. I think I forgot to ask this question, but one of the questions that I usually ask classes at the beginning of class, just so you get an idea of how my mind works regarding grading. If you get a C in the class, I usually phrase the question by saying, would you be satisfied with a C in this class? And most students, especially in calculus class, are like, oh, no, no, no. The only thing is an A. I have to get an A. That's like saying if you're going to be a professional baseball player, the only thing you'll accept is being a Major League Baseball player. And that's just like not how it works. So if I say, would you be satisfied with a C in this class? By definition, you have to say yes, because by definition, that's what C means, satisfactory. C is satisfactory performance. That's me saying, good job. That's actually not even me saying good job. That's me saying, satisfactory job, go on to the next class. So the answer is not to give everybody A's. The answer is to ignore GPA and stop being so competitive. So the comment is, unless your GPA is 2.5 in a world of competition. The answer is to stop making that part of the competition. GPA is a meaningless statistic. This is not baseball. And the only way that this is going to get fixed is for all of you to stop giving a crap about GPA. This is the only way forward. If you get to a position where you start looking at GPA, and you don't stop, then you are perpetuating the bad behavior. Here's an example of why GPA is meaningless. The highest grade you can get in this class is an A. The most grade points you can get for this is a 4. The highest GPA I could have graduated with when I graduated high school is a 4.0. That is the highest one I could possibly get. I could go through all 4 years of high school, never miss a single question, a single point, a single day of work, and I'd had a 4.0. And then I saw this article where some dude graduated with a 5.0 because every class he took was an honors class. He is literally playing by a different set of rules. You can't look at this kid and say, well, he got a 5.0, whereas Leach over here only got a 4.0. We both did the same thing. Went through our entire high school career, never missed a point. But because he was playing by a different set of rules, he gets preferential treatment. That's what I want to stop. GPA is a meaningless statistic. Your SAT score is a meaningless statistic. Unless your job is going to be to take the SAT, your SAT score is a meaningless statistic. Your honors classes should mean something more than a higher GPA. If a student comes to me and I'm like a hiring manager and I see that they have an honors class, I'm not going to look at their, I still don't care about their GPA. Tell me about the project that you did for your honors course. If you don't have an answer, you didn't really do an honors course. Do you know what I mean? I know this is America, and in America, everything has to be competition. But if you're making everything competition and the competition is not fair to everybody, then it shouldn't be done. Here's another example of grading bias that I think needs to go away. I'm not going to give you more points because I think you worked harder. I can't use effort as a basis for grading, and here's why. Some students, I see the effort that they put into the class. They're in my office every day, or I walk by the STEM center and they're always there working in groups, and I'm like, oh man, look at that can-do attitude. Look how hard they're working in my class. Probably some other class. I try to make my class easier than that. But look how hard this student is working. So what I'm doing, if I give that student preferential treatment when it comes down to grading, I am grading that student by a different set of rules than the student that can't show me all that effort. What about the student that comes to campus, then goes home because he's unavailable to come to my office hours? He's unavailable to sit in the STEM center the whole time. That student is de facto penalized because they're unable to do the thing that and they could be working the same amount of hours. They could be putting the exact same effort in, but I can see one and I can't see the other. It is unfair. Therefore, if I can't use effort to grade all my students, I should not use effort to grade any of my students. If GPA doesn't mean the same thing across the board, then GPA should not be used to judge people. And I'm not saying this because my undergraduate GPA was embarrassing. It's not even embarrassing. It doesn't matter. I graduated. You know what they call the guy that graduated last in his class in medical school? Doctor. So no, GPA is BS. Shouldn't be used. And I can tell you, like I said, I have a very bad undergraduate GPA, and there's exactly one person in the world to whom that matters. Okay, there's two people in the world to whom that matters. My GPA, I'm talking about my GPA. Yeah. I think my wife is embarrassed by my GPA. My mom, of course, thinks I could have done better. I actually don't have an answer for how we get around admission systems for UC. I think there needs to be very strong pushback versus the system that we have in place. And I think if we really push the UC on this, then the UC's answer is going to be, well, this is the way we've always done it. And at which point they need to be shamed for this, and shamed hard. So you cannot use, this is the way we've always done it, as a justification for anything. Because there's an entire gender that, if we just went with the way we've always done it, wouldn't get to vote. This needs to stop, and it especially needs to stop in schools that pride themselves on trying to teach critical thinking. You don't get to call yourself an institution of critical thinking and at the same time say, well, this is the way we've always done it. You don't get to, as an institution, recognize that the way we admit students is inequitable, and then turn around and keep contributing to the inequity. You've got to come up with solutions. I don't really care if Stanford does this. Stanford's a private institution. They could do whatever they want. But the UCs, that is our thing. That belongs to us. I'm not saying that the general population knows a better way, but I'm saying that a big group of highly educated people should be expected to find a better way. Anyway, I have my ideas for things. Like I said, I'd stop making you pay, and I would I would blow right past making it free, because free doesn't help anything. Forgiving student loans is a Band-Aid on the problem. Forgiving student loans is a Band-Aid on a bullet wound. We've got to go farther. Make this your job. If we want people to be educated, if we want people to do school, then we should just pay them to do it. If you want people to do things, pay them to do it. If you're not willing to pay people to do the things that we want them to do, then we never really got rid of slavery. I've never run for politics. It's too easy to take me out of context. Anyway, you know what I mean? So, yeah, what's the answer to inflating grades? Well, here's the answer. What if we just got rid of grades? What would you do if you didn't have grades? What would you do if you didn't have tests? What would you do, teachers? That's my question. That's the question that I think about all the time. I try to have some semblance of like normalcy with like homework and quizzes, and I'll have something that's labeled final exam, but it'll still be problems that I'm asking you to work on, and I'm going to give you multiple shots to work on them. And then teachers are going to come after me and say, oh, what are you going to do? But if the students get multiple choices, then they're just eventually going to get the answers right. To which I have to respond, isn't that the point? I keep hearing that the point is to educate the students. So we should encourage them to take risks, get things wrong so they can correct themselves and get things right. And we should reward that behavior. Otherwise, the whole education system is just aimed at students who are going to be really good at this naturally, which is exactly what the school says they don't want to do. So, dear school systems, are you ignorant or are you lying? Those are the only two choices. Anyway, enough of me ranting. But it's important for me to say these things to you because you're trying to play the school game. Your job as a student is very different than mine as the instructor. Mine as the instructor is ostensibly to teach you, but as I've explained, it's really just to put you into categories. Good student, bad student. Your job as student is ostensibly to learn, but it's really to figure out what you have to do to make the teacher write good student at the end of the semester. You know what I mean? So it's important that you know where I'm coming from and you know how I think about this process. It's important that you understand that I think grades and tests are BS and we've got to find another way. It's also important for me to realize and state publicly for full transparency that I do not know what the better answer is. I just know that this is bad. And I think part of the problem is I might just be too old to figure out a better way. So I'm just going to do the best that I can. And I'm just going to try to tell you, I do care. I want you to, I care about how you think about these things. I don't care if you can integrate some function with trigonometric substitution. I want us to do that, but I think it's unreasonable for someone to get a better grade just because they happen to be good at that. You know what I mean? I think in some ways this makes me a good teacher, and in other ways this makes me a very bad teacher. So I'm not sure what the answer is. So I'm just going to keep doing what I do until they say, no, we're going to go in this direction, Leach, you're out of here. At which point I'll just go do something else. Recognize my privilege that I can go do something else and go do something else. You know what I mean? Anyway, I appreciate you all listening to these things. I know it's not really a calculus part of the calculus class, but hey, we claim to be an institution of critical thinking, so maybe we should think critically about stuff and not just, oh, I don't know, learn how to show that a series converges or diverges. It's not about writing the argument. It's about looking at this alternating series and say the alternating part doesn't matter because of 1 over n squared, that's what wins. So anyway, that's it for today. Everybody have a good weekend as you're going through your life. I know y'all are very busy with various amounts of things, varying degrees of busy, but remember, look for the ways that things are unfair and try to fix that. Don't kick down, punch up. Never kick down. All right, that's it for today. Everybody have a great weekend. I'll see y'all on Monday, and thanks for playing, and thanks for listening. Sweep the leg. Sweep the leg.